Today's topic is tied together architecture as a living organism. So during the last years, I have built kinematic architecture installations. What you can see here is my latest project. It is an art installation at Stephansplatz in Vienna. And as you can see, it is not only lightning sculpture, it is also a kinematic sculpture that is able to change the focus of the space to different situations in the room. I'm coming from the field of architecture, but during the last years I have made a lot of projects in the digital space. So my main program is Blender 3D, and this is my connection to Python. This is, I guess, why I'm talking here to you today. I'm a self-taught Python programmer. And as you can imagine, in this kind of projects, you need different kinds of tools. So classical CAD programs in architecture do often not reflect the possibility to work with these four-dimensional sculptures, with these animation tools, with constraints, etc. And Blender is a tool, as you may know, from the gaming industry, from the film industry. And I find this very interesting to use these kinds of tools because it's not only about being able to draw 3D models that you are not able to do in classical CAD programs, but it's also a different point of view to architecture because you're not drawing an object, you're not drawing a building in these tools like Blender, you are trying to draw completely new worlds, like in films, like in movies, etc. What you can see here is part of the detail progress. Proportional editing allows us to transform geometry very freely. And furthermore, Blender 3D is able to be controlled with Python. And I'm doing all these detailed plannings in Python-based scripts that I'm writing on my own in order to manage these logistics beyond these projects. Every part that you can see in this project is somehow connected as an object in Python, and therefore I can calculate how much parts do I need of which and how to assemble them and when. So coming to the topic of today, bAm is standing for Bewegende Architektur Modul. So it means both, it's moving and it should also have this emotional character. And it's starting out with my PhD. I have done an interdisciplinary PhD between mechanical engineering and architecture. And the idea beyond this was to have a movable kinematic robot that has a simple artificial intelligence. So it is able to recognize the environment. This is 3 ultrasonic sensors that are able to have a rough floor plan of the site. There are cameras. OpenCV is used to make an image recognition. And there are microphones in order to control them by a voice. What you can see here is this simple artificial intelligence that is based on different Python modules that are handling different parts, like the movement, like the recognition, etc. The whole project is based on open hardware, so it's done with Arduino and Raspberry Pi. And the main language is C and Python. And the idea beyond this project is that they are able to recognize each other, connect with each other, and build space together. This is heavily based on the Boyd system by Greg Reynolds. Here you can see an image of how it should look like. So you have these linear actuators that allow the module to move, to lift, etc. And therefore create interactive architecture. This is another version of this robot. This is version 2 called the Spider. And this robot was mainly reduced in cost. So the idea was to use less parts, but a more complex way of movement. And the third version was again a very rough switch in the direction. It is a kinematic membrane that is able to be filled with air. These structures do have huge structural performance. So basically a cell is one of the most performative structural elements. So a cell filled with air or with fluid. And furthermore, it is very lightweighted. And I have the impression, or at least I'm think that this is a way, if we want to build more illogical with less footprint, we have to build lighter structures. So when doing architecture, we are mostly using a lot of heavy materials. And I think we should way more consider to build with lightweight structures like Frey, Otto, and other people have precasted this. Coming to this version, we have built 4 of these robots. Again, they are controlled with Arduino and Raspberry Pi. Basically, Raspberry Pi is dealing with all these internet connection, is somehow the brain of this robot. And the Arduino is handling the hardware. So there are simple Hall sensors that are measuring the actual position. Again, here the recognition of the other modules is based on OpenCV. It is a circle detection that is trying to catch the other's fear, and doing the radius of the detected circles, distance, etc., can be calculated. And today I want to show for the first time the new version, number 5. And this has, again, another principle. It is based on a zipper. And the idea is to build a robot that is able to crawl on each of their kind in order to create connected structures. And today we're going to take a look on these principles and most of all at the software used beyond it. So this is the principle. This is somehow a common model in these 3D printed zippers. So this is PLA material. If you have a thin layer, then this material is very elastic and can work as these zipper structures. What you can see here again is, is Blender that is handling these kinematics. Here, this is geometry nodes. Geometry nodes is, I'm not sure if you're aware of this node-based visual way of interacting with geometry. This is also a very good way if you are building geometry that is somehow really based on parameters where you do not have a more complex logic like conditionals, etc. One of the biggest questions was how to make these robots not only crawl on each other, but to switch sides. So what you can see here are different versions of these technical infrastructure that is used to make them walk on each other. And the idea is basically that these robots are able, like the other versions, to connect with each other with these zippers, therefore create a seamless, somehow airtight structure that is going to create space later. This is the module. You can see that there is a pump. There are 2 motors that are regulating the movement and this grabbing of the other's membranes, or maybe put this again. All these parts should be open hardware later. So idea is to make this an open source project when it's ready for publication. And today I want to show the logic with the software that is doing this simulation. So first of all, we're going to take a look at these different modules. There are 7 types that are somehow based on a kind of stem cell, and they can do different things. So first of all, there are active parts like the pump, the crawler, the base, solar, and the column, and there are passive parts like the spacer and the watcher. The spacer is an idea to have a module that has no intelligence at all. This is only moved by others and is mostly there to make the project cheaper. So there are robots that are able to reconnect the others, and the spacer and the watcher are moved by those other modules. So here you can see the idea. There is somehow this stem cell that is the basis for all of them. You have these active parts, you have these passive parts. So let's dive into these modules in detail. Here we do have a base. A base is there to create weight in order to make this structure stand on the ground. So it can be filled with rainwater or with grain found on the side. The 7 active part is the pump. This is therefore to pump air into this structure. The third part is a solar panel that is, of course, thought to create energy. You have this crawler. The crawler is able, like all other active parts, to move on the other elements. You have this spacer that is the cheapest module that is only there to create space, cheaper. You have this watcher. The idea of the watcher is to have an overall system that is controlling the others. So most of all, the idea would be to have it bottom-up intelligence, but of course there should be some system that is able to control it. And another module is the lifter that would work as a pneumatic column. The principle is based on a cloth simulation. So in Blender 3D, you have the possibility to simulate different kind of physics, different kind of, for example, fluids, smoke, etc., and also cloth. And the main idea is to use this existing bullet physics cloth simulation. So here, this ring, as you can see, is working like it would be from textile. And there is a small trick that you can do. You can create loose edges and make sewing. Sewing means that these parts are going to be dragged to each other. So these edges are going to be reduced to 0. So there is some attraction force, and an edge is trying to be dissolved until it has 0 length. And this is the main principle of this whole simulation. So the idea is to use this physics engine that is written in C++, and Python is doing all the logic beyond it. And in a way that you maybe should not copy, but of course you can, because it is, let's call it a hack. It's more like a hack, because what I'm doing here in the next step is that I'm going to change the topology of the mesh by reconnecting those edges in order to make these kinematic. This is happening in these steps here. So let's take a look into the current state of the simulation. So this is written in Python in Blender 3D. Hopefully you can see this because it's very dark. Oh, I'm not sure. Can we turn off this?
No, there's satellites.
This, okay, sorry. Hopefully you can see it. But what you can see here is the simulation. I guess it's very hard to see. Okay, it's a little bit better now. This simulation allows us to add those different kinds of modules to the scene. Here you can see the simulation running, and these models are able to reconnect all of their single edges in order to crawl on the other modules. Just imagine this like a zip tie that you can open and close, and the robot is moving on the other element by closing and opening this zip tie. And this is happening in a way that I'm only changing the topology of the mesh. So not basically the topology, only the edges and their base vertices are calculated every frame, and therefore the animation is changing accordingly to these new conditions. So as you can see, you have these active parts that are able to move on the other, and you have, for example, the bAm 0 that is only a spacer, that is only there to make the whole structure cheaper. In the next video, we're going to take a look at some code. So first of all, it is done in a way that every module is taking care of its own allocation. So there is an allocation that can be free, connected, it can be a head, it can be a tail, or it can be bonded. And the other modules is changing its behavior based on the other's state of the allocation where it's going to be connected to. So there can be 4 different kinds. The first one is that by moving forward, the head position is checking if the target position is reached. This is very simple. We only have to take the edge you have seen in the previous image and check if the edge length is beneath a given threshold. So for example, 0.05, if the edge length is smaller than this value, I know that the target is reached and that the next connection needs to be done. And the easiest way is that the other module is free. So if the allocation of the other module is free, it is simply taking the next edge of the other's ring and connecting this edge to it. So as you have seen before, you have this edge, and if you put sewing on it, it's going to be shrinked until 0. And when the other module is free, it's only taking the next edge, connecting it with their own edge in order to make the next link. The other case is that the module is hitting a head. If the module is hitting a head of other module, it has to change to the other of the other module. So just imagine the image before. If a module is taking the head of another module, of course, it has to switch to the other state. And this is happening in a way that is getting the other module of the other and putting the next allocation of the head to it. The same is the tail. This is same situation, only inverted. So if it is hitting a head, it's taking the other location of the other's module connected to the neighbor. And the last one, if it is bonded. So this is happening, for example, if a spacer is bonded with another module, it's the same situation like the head and the tail. It has to take the other's location in order to move forward on this one. And this is basically the trick that is happening here. Just be aware that this is a hack, so is another suggestion, because it's not a good idea to update a base mesh in Blender during an animation, but it's working. So basically, if you have the experience that this is suitable for you, you can do this without any errors. At least there are 2 rules that you should never break. You cannot add vertices, you cannot delete ones, and you cannot change faces. But if you only change the allocation of edges, and update the base mesh in a Blender cloth simulation, this is working. Untie is the same. If you untie an edge, you cannot simply delete it, because then in the next step you would miss it again, and you cannot create edges during a simulation. But in this way, I'm just connecting it back to the ring of the module itself. Coming to the aggregation is also in the current state can be simulated. You can define collision objects. So you're just creating a layer and say every object in this layer is a collision object. You can add these different kinds of robots, starting out with a spacer. The first module always needs to be a spacer, because otherwise you would create a head without connection. And at this position you would block the whole aggregation, the movement, because you cannot move forward if the module is not connected with another's head. So I'm sorry that you really cannot see this, but I guess I'm switching to the solid view. Sorry, it's hard readable, right? Okay, here maybe you can see it a little bit better. Much better, yes. I will upload the images. It's really a pity that you cannot see what's happening here. But actually, this is the aggregation of these modules. Coming to the next slide, creating space. This is, of course, also done with this cloth simulation. So these modules, when connected, are trying to reduce all the edge lengths to 0. And in the next step, they are lifting. So imagine this like you do know this from tennis holes, etc. So this is basically a membrane that is filled up with air. This is one of the cheapest ways of creating space, because you do not need much material, and it's a very, very efficient way of doing a structural building. This is the hardware, so just take a small glimpse into the hardware. This is also done with fritzing. This is a tool I just can suggest everyone. It's very common in doing this open hardware projects. You have the ability to produce simple PCBs that are very cost efficient. At least from my point of view, you can easily create own PCBs with open hardware projects. This is a small glimpse into the software that is also written in Python and TPG. TPG is extremely lightweighted, performant tool of doing graphical user interfaces. What this tool is doing, it is a top-down control for the robots. So you can connect with all of the robots in the LAN, reconnect them, and have this graphical preview on the right. It's done also in Py.NET. Just a small glimpse. This is very simple way of interaction. You have a while loop that is waiting for a UDP signal, and it is just, here we have the modules side of view. So the UDP is just constantly updating the sensors and the motor speed, and the other side of the module is constantly sending you orders just in a simple string way that is read as a task and executed. This is an overview of the whole software of the state right now. You have the aggregation that is done in Blender Python. This is based on 7 modules. You have a geometry module that is handling all the mesh creation, these untie and tying of the structure, etc. You have the graphical user interface. So this is a very beautiful way in Blender to create user interfaces with sliders, with buttons in order to interact with the geometry. The strategy module is this module that allows you to preview a structure on site. We have the movement. This is our own module that we have taken a small glimpse into. This is where each module decides how to climb on each other. The numbering module is only handling the labels in the whole scene. And the terminal is only a way to link the print function to a graphical version of it in order to make all the terminal outputs renderable in a scene. And the basics, Py is just a model that is working like a config file. It is storing all data that is used by all modules and all functions that are used by merely all modules. The hardware is also split into parts. There is this Raspberry Pi 2040. This is also written in MicroPython. It's very nice because you have two threads, so you can run two Python threads continuously. And the two are the main loop that is calling the hardware and is accessing the config file, and the UDP is running on another thread that is constantly looking for updates from the PC module. This is the last module. The PC module is, of course, based on a main Python file that is running a visualization done in TPG, is running the UDP module, and simulation module is storing all the logic that has been created by the aggregation module in order to execute it. So let's have a look on how this should work. So the idea is to create open source architecture that everyone can build such a module or buy such a module, can bring it to a site, and together you have this idea of a bring your own boost party. You bring your own bot, and these bots are able to create interactive space together in order to make architecture more flexible, more democratized, and more adaptive to environmental and human needs. So thank you very much for your attention. This was my talk for today. I want to just make a small preview. Carl Dykes and me, we are going to take a small step into Python programming in Blender. We have written an add-on called Phenotype, and Phenotype allows us to make structural optimization and also an genetic algorithm and a gradient descent algorithm available for structural optimization of architectural shapes. This is all written in Python in Blender. It is licensed under GPL3, just like the Blender Python. So we are inheriting this license model. So you can download it for free. You can also participate if you like. And today at 14 o'clock, we're going to take a small look in how we have done this add-on and also how to use it. So thank you very much for your attention.
So this was really interesting, but now I'm one of those guys who has a terribly practical question. When you have all these robots and they are coupled to each other, then how would you go about charging their batteries?
Yeah, that's a good question. The idea is that the membranes have two wires, copper wires, that are transporting the energy from the solar modules to the robots. This is a big question, of course. So I'm just wondering, the biggest question is how to store the energy in an ecological way. But for me, it would also be an idea that the architecture is only adapting if there is sun and if they are able to move. So this would be my answer to this question. So idea, of course, would be to have some kind of accu packs, but the modules are able to transport energy from each other. So that's the idea beyond it.
Thank you for the talk. It's quite interesting, but I'm interested in how you calculate the maximum forces allowed, or for example, if these are getting older, there might be some aging of the membranes,
Yes.
how you take this into account and how you exchange this information. Is this also exchanged over the same way that the other communication takes place, or you have some out-of-band communication for that?
Until now, I have not calculated. So, of course, I will call Coldike someday, and we are going to make an overall calculation of how much modules you can connect in order to create a space. I would see this more like a bottom up. You have a module that I'm trying to build right now in prototypes. You would calculate how much force it is able to vary, and then you would set a maximum of, okay, you can have, I don't know, 50 modules that are able to be in one row. So the idea is to switch this around, but there is no calculation until today. But in a membrane structure, there is one very beautiful thing. They are getting more efficient the bigger they are. So if you take a look at these Frei Otto structures, there are very large scale structures that are getting more and more efficient the bigger they are. And the statical performance is you can compare this to Traglufthalle. I don't know how to call this in English, but it's like a tennis court, which is you only have a membrane and you pump it up with air. But to answer your question, there is no structural analysis until now.
My question is, as pointed out, material itself begins to degrade. If you already have a structure in place, as for example, the one here on the screen, how would you go about replacing a broken membrane?
A broken membrane could easily replace because the modules are able to crawl on each other. So I completely understand your question. It would more be if a motor, for example, is broken. This would be an issue because a broken motor will lock somehow the module. But there is the possibility that another module is crawling into it and transport it. So basically, if the module is bonding the other one and is moving with the other motor, it can transport the other module. But is a very big issue that you are addressing here, because if the motor is broken, it would not be able to reconnect from the other. That's an issue, yes. So maybe there is another kind of module that is handling this situation, that is able to unlock a module, because I completely agree, if a module is, if the motor is broken, it is not able to unlock, and therefore it is somehow blocking.